concentration, which means diffusion will happen, your steel will corrode. And when steel corrodes, it's a much bigger issue. And many, if for example, if you're in a place like New York City, you just can't stop traffic in New York just because you have to clean a bridge. The overall expense if you close a bridge in New York City is in the order of hundreds of millions of dollars. They don't want to do that. So they want it as good as possible. Therefore, they drop the strength. Dropping the strength was the best option. So that there is enough relaxation in your concrete to prevent cracking. So, creep, relaxation, viscoelasticity are very important ideas when we develop. Again, goes back to materials by design. You need extremely high strength. Yes, sometimes you may need extremely high strength, but that is a very rare need. You are not going to make a concrete column the size of a pencil. You are not going to make a concrete column 2 inches thick for a high-rise building. You need a certain size for functional requirements, right? Now think of designing a concrete column. The moment you reduce the size, you have slenderness effects coming in, right? Then you want to typically design a short column, but if you have a very small cross section for a short column, it becomes a long column. When you have a long column, then you have to go to Euler theory and use buckling design and take care of all the buckling effects, right? And buckling is flexure, is tension, lot of cracking because of buckling. So now you are completely confused. Do I want high strength with low cross section, low strength with bulky concrete? When will I have a low, right? Then there's a lot of options. Again, it's a design issue that you have to be very careful with. And this is one of these creep relaxation is one of the issues where structural design and materials really come close and overlap each other. Did I tell you the story with the nuclear reactor thing where very high creep happened? Right? Very massive structure with extremely high creep, where cutting of a small portion of the concrete dome created random cracking all through because of creep. There was so much of, and very high strength concrete, there was so much of pumped up stresses. When you started to relax it by certain cutting, it just massively spread like crazy. It had so much of stress built in. Again, issue with high stress. Okay. Very similar to shrinkage, you can't recover creep also completely. You can recover some amount of creep. You have elastic recovery and then creep recovery, but then a lot of creep is irreversible. Remember, when you talk about shrinkage, creep, while you are having a creep in the concrete is also drying along with it, right? Drying shrinkage is happening, that's a volume change. Creep is a load-induced volume change. So now you have a combination of load-induced and drying-induced volume change. Remember, your drying-induced volume change takes water away from the capillary. Assume that you have greater than 45% RH. Water goes away from the capillary, and then some local redistribution of water happens. Where is the only water available now? In the gel pores and around the gel pores. And then you have mechanical loading, high mechanical loading. What will happen to the gel water? Starts to squeeze out. Gel water starts to squeeze out, shrinkage happens, right? Creep causes shrinkage. Creep causes loss of volume. And then add that to the shrinkage stresses already, you get creep stresses. Cracking is guaranteed unless there is something to relax that stresses. You have a high elastic modulus, is it going to relax? Low elastic modulus, low stiffness, you may have a chance. That is why you must try to do a balance. Now, you will tell me, yes, I want to do low elastic modulus, therefore I will throw in rubber tires in concrete, I will throw in whatever are soft particles in concrete, that will reduce my elastic modulus of concrete. And then I'll put in a very strong cement paste, and then I'll throw in these to reduce elastic modulus of concrete. Will it help? Have you changed the elastic modulus of the paste? Right? Your paste is still the same. You maybe to overcompensate for the fact that you have put in these rubber particles, you probably might have added more cement and stiffened the paste. Counterproductive, right? You actually had good intentions of making the elastic modulus low, therefore you threw in the rubber particles. So you will see these papers were saying influence of soft aggregates on creep of concrete. Nonsense. Your measured creep of concrete will be lower because you are measuring the bulk part, but the actual response is dictated by the Cement paste, if creep is a function of loss of water, your aggregates have no role in it, right? So overall measurement of creep, that's another thing that you have to be very careful. When you do this bulk overall measurements, you can tweak it whichever way it is. Like you talk about statistics, right? You can say that a century in 50 balls is really good, or you can say a century in 50 balls is such rash batting, right? You can do both ways. So statistics can go both ways. You can overall elastic modulus is lower, but what lowered the overall elastic modulus was the presence of this soft aggregates, which does nothing to creep off the cement paste, which is where the actual creep mechanism is happening. Right? So the idea has to be, so again the idea of limestone. Good idea because limestone is soft. It reduces elastic modulus of the paste. It gives you good reaction products and strength. So materials like that. Fly ash, slag, good because these are of lower density than cement, and when they react, they'll give you a little less stiff paste. Okay, so creep has also to be very carefully taken into account. Creep coefficient, creep strain, I'll skip all of that. Applied stress and creep lies in CSH. I was telling about this. I'll do some creep theories. Okay, this is the very diluted version of a creep theory. Slip between adjacent CSH particles under shear stress. All of you can relate to that? You have layers of CSH, under load, sliding, slip, easy. Depends on forces between particles, okay. Creep depends on diffusion of water in micropores under stress, disjoining effect. Where did we see the disjoining theory? Greater than 45% RH in shrinkage, right? So diffusion of water in micropores under stress, real water that is there in the pores that has re-equilibrated. That's why I told you that water will diffuse from everywhere else to the capillary area to redistribute. That redistribution also will cause creep. Equilibrium state of water determined by a combination of stress and water layer thickness. CSH particles are 5 water molecules thick, roughly 5 to 10 water molecules thick. Basically, which means if you apply enough load to squeeze 5 water molecules out, you have collapsed the CSH layer completely. Okay, so but that takes a lot of load to squeeze 5 water molecules out. Remember, because the stress required is extremely high, because the area of cross section is very low. You are almost doing this point load, so stress is infinity that's required to do this. Okay, so this is what we talked about. Water squeezed out of micropores. Where does this water go? Reordering of CSH. Like I told you earlier, there are no stress in capillary pores at all, so you just have reordering of CSH. Reordering of CSH leads to sometimes increased bonding, and under high stress, calcium hydroxide can dissolve. Have you heard of stress corrosion? Stress corrosion cracking? Corrosion can happen under stress. Similarly, calcium hydroxide can dissolve under localized stress. So when you have very high stress in this crystal, the crystal wants to dissolve to release that stresses. So you can have calcium hydroxide dissolve, and then they will redeposit. Now, when calcium hydroxide dissolves, there is calcium and hydroxide concentration, the pore solution increases. When that pore solution concentration increases and gets to saturation level, it has to reprecipitate. It will not reprecipitate at the same place, it will reprecipitate elsewhere and create the same condition at a different place. Therefore, creep is a stress-induced aging leading to the elimination of micropores. Why? Because calcium hydroxide preferentially, this area got collapsed, calcium hydroxide dissolved from there, so this pore is already gone, right? Collapsed, calcium hydroxide dissolved, precipitated somewhere else, filling in a pore there. And then this mechanism happens, creeps again, dissolves, reprecipitates somewhere else. So this process goes on, eliminating the micropore, so eliminating the really small pores, which means what? Now, think about it. Some of these micropores are eliminated, which means the remaining pores are even smaller. The same process happens along with higher stresses when water goes out because of shrinkage. Now this cycle continues. And anything in concrete, it's a series of cycles. Okay. I think that's creep and shrinkage. I have left just the mechanical and durability properties for tomorrow, which I think I can finish in 2 sessions tomorrow morning. Any questions? I think we'll maybe I'll do until 12 tomorrow, and then between 12 and 1 you can ask questions, we can have discussions whichever way you want. I think that's enough. I think by the end of today you might think of leaving here if you have not thought of already, right? At least I'm happy to see many of you have stayed back. I was thinking that in day 2, first day very excited, day 2, yeah, not bad, I can do some more. Day 3, yeah, concrete fatigue is taking over. Day 4 and 5, can we go back, right? I tell my students in classes. So we in our university, classes start at 7:30 and end at whatever, sometimes 7 o'clock, 8 o'clock in the night, depending on what classes people take. So when they have a 7:30 in the morning class, they'll say, oh, professor, too early, very tired, sleepy. 9 o'clock class, yeah, it's a good time, but my alarm didn't go off. 10:30, it's okay, but mornings are too busy. 12 o'clock noon class, lunchtime. Afternoon 1:30 class, sleepy after lunch. 3 o'clock football match starts at 4. 4:30 class, oh my God, who wants to sit at 4:30? Every day thing for you we can make a reason. A lot of students do that. 7:30 class, standard excuse I hear when I don't teach, but when other people teach at 7:30, standard excuse is alarm didn't go off. Well, you have every day your alarm don't go off, change the alarm. Right? How many times can your alarm not go off? Change it. But then, there is no need to come to class also. None of us will enforce, there's no attendance business. You come if you want. If you know whatever I'm going to teach you without coming to class, all power to you. Come do the exam. If you get an A grade without studying anything, you're super good, please get it. So 20% of people, typically 10 to 20% of people don't even show up. And many of them fail, of course. But some of them don't need it because they have other ways of learning and studying. Okay, any other questions? All good? No, you don't need 20 years. You can do a creep test in 3 months. 3 months, 6 months, 18 months, depends. If you need a creep test for 20 years, why would one do a PhD on that? I don't think anybody would sign up for a 20-year PhD. Yeah, long term, actually, what happens is creep, so you get what is called creep compliance. What you're measuring is a creep compliance, right? That's what you want. So you basically measure creep deformation as a function of time. As you go, you can kind of see this curve plateauing off, right? So there is primary creep, there is secondary creep, there is tertiary creep. Once you get to the secondary creep zone, tertiary creep is when the creep starts to induce failure. At the tertiary creep, so you don't want to do a test to a tertiary creep. I mean, you can, but you typically don't want. So one way people do it is to do it for 3 months, 6 months or so, and you get a good part of secondary creep, and then you can use models to predict further down. The other way is if you're doing creep in flexure, make a notched beam. That's a smart way of doing creep. Make a notched beam. Make a beam with a small notch. What have you done when you make a notch? You already induce a stress concentration. So you accelerate your path towards tertiary creep, fooling the material by telling that you have to fail in this notch alone. So you can do flexural strength using that. The other way to smartly do creep is to throw in some fibers so that you can have very good control of crack growth while under creep. Because when you have fibers, they bridge the cracks, right? So you can measure crack growth. If you put a notched beam with fibers, put an LVDT across the notch, you can measure crack growth while under creep. In 3 months or so of creep, you can get a lot of very good data. Okay, you don't need 20 years. I mean, why would somebody do it for 20 years? Yeah, that's because he has nothing else to do, probably. Yeah, because a lot of places, right, you put all this setup and put a specimen underneath it and log the lab and come back 20 years down the line and see what is there. I mean, there's no point in such tests. There's no point in such tests. What happens if power goes off in between and your whole LVDT and your computer system shuts down? That's it, you're done. And then you start again with 20 more years. I think some of those tests don't mean anything. I mean, we have sophisticated models, and that's why understanding what causes these phenomena are important, so that once you get a significant amount of data, you can take over and do models to fit the remaining, and that will be pretty much how it will be. And then also there is there's no point in trying to find out what's the influence of this on creep, that on creep, and all of that. I mean, people do that most of the time, but it's a phenomena that's extremely important. It's a phenomena that has a lot of relationship with the pore structure. And as long as you have control over pore structure, I think you should be okay. Self-compacting concrete. So there are, ideally, concrete is not even a Bingham model. Okay, theoretically, strictly speaking, when you say that I need a certain yield stress to start moving and immediately after that everything is linear, is not correct. So there are other models. If you have heard of Herschel-Buckley, there are other models that they use. Self-consolidating concrete also is Bingham, if you want to consider it Bingham, but with a very small yield stress. That's the only difference. A lot of people consider it to be Newtonian because it's easier to use it as a straight line starting from 0 with shear rate. But since you asked this question, I'll tell you this. The whole idea of Bingham fluid is that you need a certain shear stress to move, to start moving. How do you define movement? Right? What is movement? Does a mountain move? Does a mountain move? It actually does. You ask geologists, they'll say a mountain moves, right? It moves slightly. So the question of movement, especially in concrete, is a very difficult thing to answer. If you look at the scale of the aggregate particle, yes, it's not moving. But if you look at the scale of the cement paste, it is moving, right? So when you talk about the rheology of concrete and you say that I need a certain yield stress to move, what is moving? Is it the paste, is it the aggregate, is it the concrete as a whole? And that is why, as an experiment to do, you can get this and fit it. But realistically, the idea of yield stress, determining a yield stress through a Bingham model, again, what strain rate do you use for a Bingham model? So you do a strain rate of say 5 to 100 and then draw this line, extend this line to the y-axis, take the intercept. What is y-axis? What is a y-axis strain rate? 0. Why would I ever say that at a strain rate of 0 something will move? I haven't tried to move anything and I'm saying something will move. It's mathematically inconsistent. But it is convenient. To show somebody on a graph, it's convenient, but it's totally mathematically inconsistent, right? So I started my experiment at 5, I went to 10, I went to 20, I went to 30, I plotted all of them together, and then I extended that to 0. How can you extend an experiment from 5 to 100 to 0? Because 0 is a very unique number. 0 is a very unique, how do you extend it to 0? And then at that 0, you say this is my yield stress, because that's what it takes to move. Hey, at 0 strain, you haven't applied anything to move, then why is it moving? Black magic? So that's why these tests, people don't ask these questions. I mean, everybody writes it. I also have done this. I also have reported Bingham yield stress and then moved on. Opportunistic, wants to get things done. But strictly that's not correct. So what you should do, realistically, you should have a very good rheometer that can take you to strain rates of say 10 to the minus 3. 10 to the minus 2, 10 to the minus 3, really slow, very slow shearing. Find out what is, and you will see that the line that you draw like this and extend to 0, actually if you expand that little portion between 0 and where you started the measurement, you will see the line becomes a plateau. That plateau is the actual yield stress. That is what the material is saying is its yield stress. That is the exact value. If the exact value of yield stress, because at very slow shear rates, you always have a plateau because something is moving. It's never 0. You have it slowly moving. You find out that, and then it starts to pick up at some number when lot of reorganization has happened. And it's not very difficult. When we have done that, after that, consistently we have done that. You can't do it for concrete, you can do it for cement paste very easily. So the idea that shear stress at a strain rate of 0 is my yield stress is a bogus, fake. It's a convenient number, of course. I mean, no question. You can compare it between different systems. It's a convenient number. You can plot nice bar charts and show somebody. I even showed you 500 kilopascal, 50 kilopascal, 5000 kilopascal. We do it. But it's strictly not a very good thing. There is absolutely nothing called zero strain. When you have the minuscule movement happening, there is strain, right? And even your lifting of slump cone is introducing a strain in the particle around, right? So there is nothing called a zero strain. And it's again, like I said, convenience. Now, do you want to really split hairs on that? No. Do a slump measurement, do what the slump flow is, do an L box test, do a J ring test, do whatever, and explain it, and that's fair enough. I mean, you don't have to really go, but if you really want to explain what is happening in the fundamentals, I'm sometimes talking like a physicist, because you know, engineers do a lot of approximations. In real physics, the number of approximations are low. So can we extend to that? Yes, but do we really need it? Probably no. I mean, I can go and talk off the top of my voice about how slump test is bad everywhere, and everyone will agree with me. Will anybody stop doing it? Everybody. I can guarantee you, I can give the same talk. Everybody who has common sense will agree with me that yes, it's a bad test, it doesn't tell me anything. Can I make one guy stop doing slump test? No. That's a state of the field. So sometimes there's a disconnect between state of the art and state of the practice. That's why you always say, right, what is state of the art and what is state of the practice, and you say state of practice lacks state of the art by, in our field, by a generation. If you're talking about computers and chips, state of the art, state of the practice lacks state of the art maybe by 2 years. If you look at space technology, state of the art lacks the state of the practice by 3, 4, 5 years. We lag by a generation. I mean, is it really important? I don't know. Now we have 3D printing, concrete being 3D printed. You've seen pictures where people 3D print concrete houses, right? So the idea apparently is there's a competition in the US, NASA competition on 3D printing for Mars. I had a very simple question to one of those guys who said, 3D printing for habitat in Mars. I said, everybody is taking a one-way ticket to go and die. Why do you build something there? Just go there, sit there, you'll be burned off and they can be happy. Right? So they are trying to use Martian materials to build houses in Mars. So Mars has a lot of, I mean, you can't take cement, ordinary Portland cement on a satellite, on a rocket here and deliver it there, right? So they want, and there's no water in Mars now. They say there's water underneath, but there's no water in the liquid form. So you need to have reactions that are mediated in the absence of water. And they want 3D printing to create. So basically the idea is to send a very customized 3D printer up to Mars. Nice fancy stuff though. Very customized 3D printer, and then use local Martian materials, and this 3D printer will be equipped with some reactions, even plasma rays and stuff, that they can ionize certain Martian materials and join things together and create buildings to colonize Mars. Because the idea also is very, very interesting, right? So Elon Musk, all of you have heard of Elon Musk, the guy behind Tesla. He is a big Mars colonization guy. His argument is, if something happens to humanity, a natural disaster, some massive disaster comes, and if the humanity is going to be wiped off from the planet, I need to send 100,000 people quickly to Mars so that our footprint remains and generations can remain. Okay. When you have too much of money, you become mad. It's an evacuation plan out of the earth and go somewhere else. Yes. Yeah. So now they're looking at moon as a midpoint, as refueling station, as a sandwich place to eat before you get to Mars. So you can do land in the moon, spend some time sightseeing, like if you go to Bombay, you land in Bangalore and then go to Bombay. So land in moon and then go to Mars. A lot of different things. Oh, have you guys